Kia ora koutou, ko Warwick Whenua. I'm a scientist from the Bioeconomy Science Institute, and I'm delighted to be able to present to you today a research project in collaboration with NIWA, looking at the ecological impacts of Cyclone Gabrielle. I'll spare you the details about the event itself. Suffice to say that we often think about cyclones or hurricanes as being events associated with wind, thinking about palm trees blowing sideways in Florida or the Gulf of Mexico. And we did have localized extreme wind in New Zealand that this figure shows, but really it was more of a rainfall event, Cyclone Gabrielle in this instance. And it was really localized again in the East Coast region, specifically Hawke's Bay and Tairāwhiti receiving huge amounts of rainfall. And that drove a lot of the impacts that I'm going to talk about today. And this cyclone caused around $9 to $14.5 billion worth of damage when combined with cyclone hail and the Auckland anniversary flood. So it was a really extreme weather sort of summer in 2023. And this is likely to continue into the future. Cyclones are predicted to become more intense on average. And there's also evidence suggesting that they're shifting polewards, so towards higher latitudes. And so this means that New Zealand might experience more intense and similar frequency, if not more frequent, cyclones in the future. And so Cyclone Gabrielle provides this unfortunate opportunity to prepare for future extreme weather events by understanding which ecosystems are most at risk and how we might best help promote their recovery or facilitate mitigation when future events occur. Before I kick into the research itself, I think it's really useful to think about what's changed in New Zealand since human colonization. This is what New Zealand might have looked like before humans. Forested hills and gullies all the way down to the riverbeds, and even the river floodplains would have been forested as well for the most part. We've changed the landscape a lot. This is present day Hawke's Bay. You can see largely deforested. The hill country is mostly in pasture and increasingly in exotic plantation forest as well. So really big changes occurred in the landscape. And this has obvious implications when it comes to extreme weather events. This is an image from Cyclone Bowler, March 1988. You can see big erosion scars across the landscape. 35 years on, we appeared to have not learnt a lot. We see the same thing happening again in Cyclone Gabrielle. Again, large erosion scars on the pastoral landscape. All of that eroded soil is flowing down into the awa, into the rivers, and then that can be flowing out across the landscape and all the way out into the ocean. So Manaaki Whenua was funded by MB through the Extreme Weather Platform and in collaboration with NIWA to assess the ecological impacts on our native ecosystems of Cyclone Gabrielle. We had three main research objectives. First one was to identify changes in extent and condition of vegetation cover. The second was to evaluate impacts on wetlands and other naturally uncommon ecosystems like sand dunes and braided rivers, and then to assess resilience of freshwater fish and invertebrate communities, which was NIWA's part of the project. This map shows an overall sort of picture of the research program, the different symbols representing different ecosystems or different sub-projects within the overall program. The key thing to take away here, I'll let you interpret those in your own time, but the key thing is basically where we did the work. You can see a large amount of it concentrated in Hawke's Bay and Tairāwhiti, and then also Auckland and Northland. And this was in relation to where the biggest impacts of the cyclones were, so we were measuring those. And this is an opportunity to just say a big thanks to all of the different organizations involved that helped make this possible, providing data, providing access to the land, just providing thoughts on the ground of what had happened so that we could come in and collect the most useful data possible. So on to the first objective. This was to identify changes in the extent and condition of vegetation cover. We were lucky to be able to work with other colleagues at Manaaki Whenua who had been funded through the Ministry for the Environment to do a rapid assessment of damage to land. So they took some aerial imagery from before the cyclone, compared that to aerial imagery after the cyclone, and looked for areas where the pixels had changed from being green, vegetation, through to brown, being eroded or having sediment deposited. And so this was what that resulting map looked like. Darker red areas represent larger proportions of new bare ground, which was sort of the measure of damage in this case. This resulted in about 300 million tonnes of sediment was the estimated amount of erosion occurring in this region that was assessed. And the cool thing done here was that they took that damage map and intersected it with the land cover database to try and understand, well, which sort of ecosystems had the highest probability of erosion. And so this is just presenting data from a couple of districts, but it was a common sort of theme was what we saw was that the high producing exotic grassland and the other sort of transformed ecosystems, so exotic forest, especially that had been recently harvested, they were the most prone land cover types to erosion. And when we compare that against indigenous ecosystems like mature forest or early regenerating forest, dominated by Manuka and Kānuka, we see far lower probability of erosion scar occurring in those land use types. So really quite a strong contrast between native ecosystems and their resistance against erosion versus those transformed ecosystems. Another colleague, James McCarthy, used that same damage layer and wanted to understand how was that damage apportioned at different distances from rivers. So this is looking at that sediment flowing across the landscape, right? And no big surprises, but you did see much higher proportions of new bare ground closer to rivers than further away. But even 100 to 500 meters from the rivers, 2% of the land was a new sort of bare ground or erosion or sediment deposition. As you can see from this aerial imagery, quite substantial impacts where those rivers burst their banks and left behind a whole lot of sediment. And we started hearing reports about this sediment having impacts on native forests that occurred beside waterways. This is a photo sent from November 2023, so about 6 months after the cyclone, from Kiwi2 Rep Malcolm Rutherford. This is a Kiwi2 covenant about 45 minutes northwest of Gisborne. And you can see some discoloration of those trees looking like they're starting to die. And then you get an updated picture from April 2025. That's a huge mortality event of mature Kahikatea forest. This kind of looks like a bleached coral reef to me. So those trees are dying. They're being choked by the sediment that was deposited up to 70 centimeters deep at this site. This is the same site, but photo points from inside the forest. 2 years prior to the cyclone, you can see a nice developing understory with divaricating shrubs, mosses, all sorts going on, and they're mostly looking pretty native, pretty good. 6 months after the cyclone, it's absolutely wiped out. That understory is gone. Remember, the canopy is slowly dying as well. And then if we look at April 2025, what's coming back? Well, a whole lot of pasture grasses, a whole lot of other non-native herbaceous species. So that forest, that canopy is dying, and it's not being replaced. And so it's likely that this forest, if not managed, could turn into pasture in time, and you lose that really nice patch of forest, covenanted forest, entirely. And so we thought this is concerning. This is a regionally rare ecosystem. There's not a lot of these lowland forest left in Tairāwhiti or Hawke's Bay. So we formed a group who were going to collect some data to quantify what was going on. So this is a collaboration between multiple groups of mana whenua, Kiwi2 National Trust, Gisborne District Council, and Manaaki Whenua, lots of really key people who helped facilitate access to sites, collect data. And so we spent a couple of weeks in the region installing permanent forest monitoring plots, 41 plots at 19 sites, and we worked closely with locals to collect those data and put those permanent plots in, helping train up people so that they can be remeasured in the future, for example. And so we went to these sites and we measured the impacts of the cyclone in terms of the flooding height and the sediment depth. And we also measured the health of the rako, or the trees that were there as well. And so we gave each tree a dieback score ranging from 0 being a healthy tree that didn't look like it was affected or suffering any stress, through to trees that were recently dead following the cyclone, and compared to trees that had been dead for a while, you could tell, they're rotting. And then minor and major stress in between. And so we measured flood height by basically looking for hanging debris in the trees. This was detected up to 3.5 meters high at some sites. So a huge amount of water going through some of these forests immediately after the cyclone. And interestingly, we found that there was no relationship between the height of the flood and the mean dieback score of our forest plots. And we're not sure, maybe this is because the important thing would be how long the water stuck around, not what its maximum height was. And we don't have that sort of data. But what we did measure also was the depth of the sediment. And we did that simply by digging holes and then measuring the depth of the sediment that was deposited on top of the organic, the darker soil layer that was existing before the cyclone. And you can see there's a really strong correlation here between the mean dieback score of the plot. So dieback increases as you have deeper sediment. And this is because that sediment chokes the trees. It means that gas exchange cannot occur. And so they just slowly die. And so once you get sort of above 30 centimeters of sediment, you're looking at mean dieback scores of major stress and above. And that's quite concerning for the future of these forests. What we did find was that the effective sediment did vary among different species. So Titoki, for example, didn't have a relationship between its dieback scores and sediment depth, but Kahikatea and Matai did. And we looked at this for about 15 different species that we had enough data for. So this is just some examples, but this could be useful if you're engaging in afforestation projects in the future where you want to know, well, which are the more sediment tolerant species that I can plant in areas where I think I might get flooding in the future. And sediment deposition in the future. What's unknown is whether or not some of these trees that were stressed are going to recover or whether they're going to proceed further on and die. And so this highlights the importance of potentially going back in the future in a few years and remeasuring these plots to see, well, has that progressed to mortality or is there recovery going on, both for the adult trees and also what's coming through in the understory. And so we started to get an idea of that by looking at the understory as well and asking whether or not forest regeneration was occurring. What we did find was that in forests that were fenced and stock were excluded, there were 5 times more native saplings. So this shows this sort of importance of preventing stock access to these forests if we want regeneration following these sorts of extreme weather events. And in sites where stock access was allowed, and there was canopy dieback occurring, we saw this common theme of weeds becoming a problem, especially pasture grasses and other herbaceous species taking over in that understory and potentially replacing the forest. And so what we really want is fenced forests that have a regenerating understory that allow some resilience to these future extreme weather events. Because if we leave our forests unfenced, like this one on the left that looks like a pretty English woodland, it's not functioning as it should, and it's not replacing itself when those large trees die. On to the second objective, evaluate impacts on wetlands and naturally uncommon ecosystems. So wetlands during Cyclone Gabrielle, they held a huge volume of water. This picture on the left of my colleague Paul, he's standing up to his waist in water 6 months after the cyclone. And when this site was first established for monitoring, you could walk around in it without needing gumboots. So that just shows the difference in water levels at normal times versus after extreme weather. And a lot of these data were provided by Hawke's Bay Regional Council, Annabel and Jess Copsey specifically. This is some water pressure meters from one wetland showing 2 massive spikes, Cyclone Hale followed by Cyclone Gabrielle. The key thing here is basically these wetlands perform that ecosystem service of holding water, and while it's in that wetland, it's not running across the landscape and causing erosion. It can be released more gradually, and you don't get that massive erosion scars occurring beneath these places. The other cool thing was that these wetlands were not only providing that service, but they were largely resilient to the impacts of the cyclone. So Hawke's Bay wetland condition declined by only 5%. So this is a measure of, it's a qualitative measure of wetland condition that considers a range of factors like connectivity, predators, sediment inputs, nutrient levels in soil samples. There's about 25 different measures that get combined into this metric of condition. And really quite stable despite the extreme weather. And the same for Auckland, no decline in the average wetland condition score there. And the decline in the Hawke's Bay was largely driven by sedimentation and damage to vegetation. And you can see that in this photo of one of the Hawke's Bay wetlands. You can see erosion in the foreground where there's a slip. You can see erosion on the hillside in the background. And some of that sediment is flowing into the wetland, and that causes a decline in the wetland condition score. Another naturally uncommon ecosystem with some great data was Hawke's Bay's braided rivers. So this was a project that had been going for a few years before the cyclone, led by, again, Hawke's Bay Regional Council and in collaboration with Nikki an independent ecologist. They'd been surveying 292 kilometres of braided riverbeds for 3 years prior to the cyclone. And along there, they've been counting every bird encountered in a full census, focusing mainly on waders, but counting everything, and also measuring the vegetation cover and the cover of different substrate size classes from silt through to boulders. And if we look at so we help them remeasure the distance of river after the cyclone, so we could compare the habitat change and the impacts on the bird species. So what we saw, if we look at the substrate size classes, this is pre-cyclone data. The warmer colours represent finer substrate, the cooler colours represent coarser substrate. And then if we look at post-cyclone, we see a huge increase in fine substrate, especially in the Naruroro and the Tutaikuri. And we see this reflected in birds as well. So this is the data for pohowera or banded dotterel. They declined by 15% overall compared to pre-cyclone numbers. And this was, again, mainly in the Naruroro and the Tutaikuri, where we saw that big change in the amount of fine substrate. And we saw similar patterns regardless of which wader you looked at. Black-fronted dotterel down 30%, pied stilt numbers down 16%, and South Island pied oyster catchers declined by 43%, but this was quite a low sample size for them. The final objective was to assess resilience of freshwater fish and invertebrate communities. This was NIWA's part of the project. I'm not a freshwater ecologist, so I'm not going to share their results today, but I think this picture again kind of tells 1,000 words. So you can see the Mohaka River, the Wairoa River, sort of soon after Cyclone Gabrielle, so much sediment flowing down and these big plumes going out also into the marine environment. And so this had some short and medium term impacts that were quantified on freshwater ecosystems. Cindy Baker led this work and it's part of our report, so I'll link to that at the end of the talk. And then the marine ecosystems also had some great research done by other scientists at NIWA as well, so you can reach out to them if you want more info on these different ecosystems. So overall, Cyclone Gabrielle was characterized by not by wind, but by extreme rainfall and the subsequent erosion and sediment deposition across the landscape. These ecological impacts were likely exacerbated by the historical land use change from forested native forests through to pastoral landscapes and exotic pine plantations, and the current management practices as well. So additional pressures like invasive weeds and animals could alter or prevent recovery of these affected ecosystems. So this was again thinking back to the importance of fencing to keep out stock and even feral ungulates so that these forests that are impacted could recover. And I really want to highlight the importance of the long-term data sets that we were able to use. Without these, we wouldn't have been able to have a pre-cyclone baseline against which we could measure. So this really highlights the importance of these long-term monitoring projects. And I just want to finish up with sort of a thought about, well, where to from here? I think we really need to start considering whole catchment resilience and stop thinking about different ecosystems or land use types independently. They're all intertwined and all sort of impacting one another in their own ways. I think we need to protect and restore wetlands for flood and erosion mitigation. We see how important of an ecosystem service they provide and how resilient they are. Protect and restore native vegetation. This clearly has lower erosion risk and will help reduce future erosion and downstream sedimentation across lowland ecosystems. Fence to prevent stock and feral ungulates. This will help promote natural regeneration and those ecosystem services that come with that. And then monitor for weeds and act swiftly to prevent their establishment and spread. We know how vulnerable these disturbed ecosystems are to invasion. So yeah, again, huge thanks to all that were involved, the stakeholders, co-authors, field technicians who helped collect the data, and all the different organisations who allowed us to use their data or access to the land. If you want more information, you can download the report by using this QR code. There's some great report summary and infographics as well, which can provide some quick sort of highlights of the research too. And feel free to reach out to me as well if you have any questions. Really thanks for your time, and I hope you enjoy the rest of the symposium.